Have you ever wondered why generative recommendation systems, which have absorbed so many ideas from large language models, haven't really benefited from one of the most exciting tricks in the LLM playbook, namely chain of thought reasoning? That's the puzzle at the heart of the OneReason technical report from Kuaishou, and the answer turns out to be far more interesting than just scaling up another model. Let me set the stage. Kuaishou's OneRec family of generative recommenders, which now powers short video, live streaming, advertising, and e-commerce on their platform, treats recommendation as a sequence generation problem. Items are encoded as discrete itemic tokens, and the model is trained to predict the next item the user will engage with, much like a language model predicts the next word. This approach has shown the same beautiful scaling behavior we know from LLMs, where bigger models trained on more data consistently get better. But when the team tried to add the second magic ingredient from modern LLMs, the think-before-answer paradigm popularized by OpenAI's O1 and DeepSeek R1, they hit a wall. Their earlier attempts, called OneRec Think and Open OneRec, could produce chain-of-thought traces, but enabling thinking mode didn't actually improve recommendation quality compared to direct decoding. The reasoning was decorative rather than functional. To understand why, the authors turned to a parallel struggle in multimodal language models. When a vision language model is asked to reason about an image, but the visual and text modalities aren't deeply aligned, the model tends to fake it. It reads surface-level visual text instead of genuinely reasoning about what's in the picture. The fix requires two things working together: perception, meaning the model must genuinely ground visual content in language, and cognition, meaning the chain of thought itself must follow a coherent, course-defined logical structure. Think of it like a detective. If they can't actually see the crime scene clearly, no amount of clever deduction will help. And even if they see everything perfectly, jumping to conclusions without a disciplined investigative procedure leads to wrong answers. You need both clear perception and disciplined cognition. The authors argue the same applies to recommendation. Itemic tokens need to be deeply grounded in natural language semantics so the model can actually reason about what an item is. And the chain of thought needs a recommendation-specific structure that respects how user interests actually work. Crucially, recommendation reasoning is abductive rather than deductive. There isn't one correct answer derivable from premises. Instead, the model must hypothesize latent interests from noisy behavior, model how those interests evolve over time, and justify why a specific candidate fits the current context. This insight drives the entire architecture of OneReason, which decomposes recommendation reasoning into four diagnostic capabilities they call R0 through R3. R0 is perception, grounding itemic tokens in semantic content. R1 is derivation, reasoning from individual items to item-to-item relations. R2 is evolution, treating user interest as a temporal process. And R3 is the integrated recommendation decision itself. They built a benchmark called OneReason Bench around these layers, and importantly, they describe it before the model, because every training design choice was motivated by gaps the benchmark exposed at specific layers. Now let's go deeper into how they actually build this. Pre-training organizes data into four progressive granularities, moving from microscopic to macroscopic. At the token granularity, they don't just align each subtoken with a meaning. They explicitly teach the model how subtoken semantics compose hierarchically. For example, given a prefix pair of subtokens, the model must predict the combined semantic meaning, and it must also work the reverse direction, grounding a textual concept back to the right subtoken prefix. This is like teaching a child not just what individual letters sound like, but how letter combinations build syllables and how syllables build words. At the item granularity, they coarse-grain captions to match what three subtokens can actually carry, removing fine details like OCR text or exact prices that the compact codes can't faithfully represent. Forcing alignment with overly detailed captions would teach the model to hallucinate, so they deliberately strip captions down to category, brand, target audience, and key attributes. At the relational granularity, they construct interleaved sequences of itemic tokens and natural language explanations that articulate why one item leads to another, building a global item graph, and sampling subchains with an interval to ensure that the relations aren't trivially obvious. At the user granularity, they reconstruct full user histories with profiles, sometimes grouping behaviors by domain in multi-turn dialogues, and sometimes interleaving them chronologically across domains. They also probabilistically replace some itemic tokens in these timelines with text captions, forcing the model to seamlessly integrate the two modalities. The ablation shows that each granularity contributes a distinct capability, with user granularity data acting as the final integrator that brings everything together. Supervised fine-tuning then builds the cognition layer on top of this perception foundation, with separate task families for each of R0 through R3. The most interesting piece is R3, the recommendation chain of thought itself. The authors treat reasoning as a two-axis compression, followed by a transition judgment. The first compression axis extracts a persona type, things like stable preference priors, life stage clues, price sensitivity, even shared device ambiguity when multiple family members use the same phone. The second axis extracts interest evolution motifs, like a triggering search followed by need expansion, or a scenario continuation from content to product purchase. The motivation here connects to the information bottleneck view of representation learning, which says useful representations preserve prediction-relevant information while suppressing noise. The model first compresses the noisy behavior log into a compact, typed user state, then expands a small number of candidate interest hypotheses, and finally commits to the most plausible one based on evidence strength, recency, temporal continuity, and persona compatibility. Interestingly, when they ablate how broad the expansion should be, they find that keeping the candidate set small, around 1 to 5 hypotheses, consistently beats wider expansions of 10 or 20, because too many weak branches dilute the strongest transition signal. Reinforcement learning is where things get unexpectedly tricky. The authors find that when they do multi-domain mixed RL, thinking mode still underperforms non-thinking mode, but when they restrict RL to a single domain, thinking consistently wins. This motivates a specialize-then-unify strategy. They first run domain-focused RL to fully unlock thinking mode benefits within each domain, then use either rejection sampling fine-tuning or multi-teacher on-policy distillation to balance across domains. Equipped with this recipe, OneReason finally achieves a thinking mode that beats non-thinking mode across Kuaishou's real-world benchmarks. There's also a fascinating side observation. Even when you're going to deploy in non-thinking mode for latency reasons, training on chain-of-thought supervised data can still improve non-thinking inference compared to training on equal amounts of direct answer data. The authors are careful to call this behavioral evidence rather than proof, noting that they can't yet identify whether the gain comes from compression, reasoning, or their interaction. It's a tantalizing hint that thinking supervision leaves useful traces even when the model is later asked to answer directly. As for limitations, the paper is honest that the gains, while real, depend on careful staging. The fact that mixed domain RL initially hurts thinking mode suggests reasoning quality is fragile and easily disrupted by competing objectives. The reasoning traces themselves rely on a powerful teacher, LLM, to write and filter chains of thought, raising questions about how much of the quality is bottlenecked by that teacher. And the abductive nature of recommendation reasoning means there's no clean ground truth for what a correct reasoning trace looks like. So the evaluation leans heavily on downstream recommendation metrics and LLM as a judge protocols, both of which carry their own biases. Now let's walk through some questions you might have after hearing all of this. First, why doesn't naive chain of thought work for recommendation when it works so well for math and code? The key is that recommendation has no deductive ground truth. In math, intermediate steps are constrained by logical rules, and there's a verifiable correct answer. In recommendation, the user's true intent is hidden, and there are many plausible next items. So if the model's itemic tokens are just opaque IDs without semantic grounding, the chain of thought has nothing meaningful to reason about. It ends up generating fluent-sounding text that doesn't actually constrain the final answer. That's why perception alignment must come first. Second, why does compressing the user history into a small set of hypotheses actually help, instead of just feeding the model everything and letting it figure things out? Long user histories are full of noise, routine browsing, accidental clicks, repeated exposures. If the reasoning trace tries to consider every behavior, the strongest signal gets drowned out. Compressing into typed persona states and a handful of evolution motifs is essentially the model performing the hard part of recommendation cognition upfront, deciding what evidence matters. The ablation showing that 1 to 5 hypotheses beats 20 confirms that breadth beyond a point becomes noise rather than coverage. Third, what's actually different between training data at the 4 pre-training granularities? Aren't they all just item text pairs? The granularities differ in what semantic structure they teach. Token granularity teaches how sub-token codes compose into item meanings, like phonemes, into words. Item granularity teaches the mapping between a full item code and its coarse-grained description, deliberately matching the resolution of the 3 subtokens. Relational granularity teaches why one item naturally leads to another through explicit natural language bridges. And user granularity teaches how a sequence of items unfolds under a personalized context. Each one is a different alignment task that fills a specific gap, and the ablation shows each contributes distinct capability rather than just more data volume. So how does any of this transfer to a production recommendation system serving hundreds of millions of users? Several ideas are immediately useful. The 4 granularity pre-training data design is directly transferable to any system that uses learned item embeddings or semantic IDs. If you're training item representations purely from interaction sequences, you're leaving compositional and relational structure on the table. Adding explicit relational granularity data, where you articulate in natural language why one item leads to another using global co-occurrence graphs with interval sampling, is a concrete recipe for grounding collaborative signal in interpretable semantics. The persona plus evolution compression framework for user modeling is also practically useful. Production systems often struggle with long, noisy user histories, and the 2-axis decomposition into stable persona priors and recent evolution motifs is a clean way to structure user encoders. Even if you don't deploy chain of thought at serving time due to latency, the finding that chain of thought supervised training can improve non-thinking inference suggests using teacher-generated reasoning traces as auxiliary supervision during training, then distilling into a direct decoding model for serving. Finally, the specialize-then-unify RL recipe matters for any multi-domain platform, where mixing reward signals across short video, live, ads, and commerce naively can drown out domain-specific reasoning, while domain-focused training followed by distillation preserves the gains.